So now we'll see solving of first order and first degree differential equation and using the four different methods which we have. So let's see all the four methods which we have. The first method is the variable separation method. Variables separation method. And secondly, it is this is solving through variable separation method, and secondly it is solving of homogeneous differential equations. And thirdly, it is solving of non-homogeneous differential equations. And fourthly, it is solving of linear differential equations. So each of them has their own method. So this first order and first degree differential equations are solved using four types of methods. One is solving through variable separation method, and next is solving of homogeneous differential equations through a particular method, and next is solving of non-homogeneous differential equations using its respective method, and finally solving of linear differential equations using its own respective method. So let's see these four methods, starting from variable separation method. The first method is variables separation or separable method. So let's see how this method helps in solving the first order and first degree differential equation. As the heading itself says, variable separable method, it is very important we separate the two variables x and y in the first order first degree differential equation. So the method is about separating the variables and then solving respectively. So for example, I have the question which says solve the differential equation dy by dx equals e power x minus y plus x squared e power minus y. So I would like to solve this first order first degree differential equation in independent variable x and the dependent variable y. So in order to solve this, let me take the differential equation this modified with. Now my task out here is to take all y variables to one side and x variables to the other side. Therefore, I split all x and y variables because the method is variables separable method. I split all the variables which can be split as this using the law of index. A power m times a power n is a power m plus n. So separating this and writing this in the form x squared in this. Next, I can take e power minus y common, where I get dy by dx equals e power minus y, which is common, and I get e power x plus x squared inside. Now, all x terms I would like to take to the left and all y terms to the right. Therefore, this reduces to e power x plus x squared dx with e power y dy, because this as 1 by e power y gets cross multiplied as e power y dy. Now clearly I see that all x terms are on the left and all y terms are on the right, and hence this is separated into two variables from the given differential equation. Now once this is separated into variables, we integrate on both sides with respect to x. Integrating both sides with respect to x, we get integral of e power x plus x square dx is equal to integral e power y dy, which on splitting gives us integral e power x dx plus integral x square dx is integral e power y dy, which on further simplification gives integral e power x is by standard formula e power x, and integral x square using integral x power n by n plus 1, we get x power 2 plus 1 by 2 plus 1 equals e power y plus c, using the constant of integration plus c. Therefore, this can be written as e power x minus e power y plus x cubed by 3 equals, this is called the solution of the given differential equation. Therefore, the solution of the differential equation dy by dx equals e power x minus y plus x square e power minus y is e power x minus e power y plus x cubed by 3 equals c. C is the arbitrary constant or the constant of integration. Is how we do using the variables separation method. Now that we have discussed about variables separation method, now the biggest question which comes out here is, can variable separation method be used for any differential equation or for solving any differential equation, is the biggest question out here. So let's discuss the limitations of variables separation method. Say for example, I want to solve the differential equation dy by dx equals 2x minus 3y using variable separation method. Then I cannot solve this using the variable separation method because this particular differential equation cannot be split into all x variables and y variables aside. So this cannot be solved using variable separation method, because simply since the variables cannot be separated, into left hand side and the right hand side. Therefore, the limitations are that variable separation method can be used only for those differential equations where all x and y variables or all dependent and independent variables can be split aside. So the limitations are that variable separation method can be used for solving the differential equation only if the variables can be separated, is how we understand, and hence can be separated only then the variable separation method can be used for solving the differential equation only if the variables can be separated. Cannot separate the variables, cannot use variable separation method. Is how I understand the limitations or the learning outcome of variable separation method. Before we discuss the second method of solving the differential equation of first order and first degree, let's discuss about the concept homogeneous functions. What do we mean by homogeneous function is the biggest question in the definition. So as we know that homogeneous is something like equal in all respects, therefore equally distributed, then homogeneous function has its own mathematical definition. A function f of xy is said to be homogeneous in two variables is said to be homogeneous if I introduce the concept of k, which is equal to k power alpha of f of xy, is how I understand the homogeneous constant. So this is called, then that implies f of xy is called a homogeneous function of degree alpha in two variables x and y. So when I want to check for homogeneity of the function, I simply check for f of kx ky should be equal to k power alpha times f of xy, where alpha is a real number. Is how we understand the homogeneous function definition. So let's identify some functions to be homogeneous or non-homogeneous as related problems using the definition of testing for homogeneity. Now let's try to do this problem where the question says, is the function f of xy equals x square y plus y cube by x cube minus this. So I would like to check for homogeneity of this function. Is the function this homogeneous is the question. So let's test for homogeneity of the function. The given function clearly out here is given as f of xy equals x square y plus y cube by x cube minus 3x y square. Now in order to test for this function to be homogeneous, I use the test for homogeneity, where using the test for homogeneity I consider f of kx ky and then test for homogeneity. So in place of x I have kx, in place of y I have ky, which gives me on the right hand side x is replaced with kx and y is replaced with ky, and let's simplify this. So x being replaced with kx and y being replaced with ky, and similarly y cube being replaced with ky cube, and whole by, similarly with the denominator, x gets replaced with kx as whole cube minus 3 times kx and ky is what we get. Now simplifying this further, I get this as k square x square times ky plus k cube y cube whole by k cube x cube minus 3 times of k cube, k times of k square is k cube, and x y square. So therefore, I take k cube common here and I get x square y plus y cube, and again I take k cube common in the denominator, I get x cube minus 3x y square, so that this gets cancelled, and therefore I get this to be k power 0 times of f of xy, because this is the original function f of xy, that is k power 0 when I cancel. Therefore, f of kx ky is k power 0 times f of xy. Therefore, f xy given by x square y plus y cube by x cube minus 3xy square is a homogeneous function of degree 0, because it's simply 0. So the given problem, x square y plus y cube by x cube minus 3x square 3xy square is a homogeneous function of degree 0. Is how I understand the homogeneity of the function connected with the test for homogeneity. Now that we have discussed about homogeneous function using test for homogeneity, the other alternative method through which we can test for homogeneity is identifying through equal powers of variables. Say for example, I have the function f of xy is x square plus 3xy plus y square. Then clearly, instead of calculating this through f of kx and ky, I can directly test for homogeneity through equal powers of variables. Now as I see that the highest power of this variable is 2 and the highest power of this variable is 1 and 1, that is 1 plus 1, which is again 2, and the highest power of this is also 2. I see that all are equal. Therefore, if we get each term with equal powers, then I can say that implies f of xy is a homogeneous function, since equal powers of 2 is how we identify. Let's take one more example and see if this is homogeneous. Now clearly I can see that each of this has unequal powers, because this has power 1 and this has power 3, and the next term has power 0 and the next term has power 2 for its variables. Therefore, this is not a homogeneous function. And I have this f of xy Now I have this problem. Let's see if this is homogeneous function. Now clearly I see that this function has various terms. By going by term, the power of this is 2 plus 4, the highest power as 6, and then the next term has the highest power as 6, and even the next term has highest power as 3 plus 3, which is 6, and the next term, which is 1 plus 5, which is 6, and 5 plus 1, which is 6, and this is 6. Now since each of the terms has equal powers, I can say that because of this equal powers, directly f of xy is a homogeneous function. But degree of the homogeneous function will be 0 because all the x and y terms get cancelled. So it's a homogeneous function of degree 0 because each term of the variables has equal powers as 6. The next concept connected with homogeneous function is homogeneous differential equation. So now that we have discussed about homogeneous function, a differential equation of first order and first degree which involves homogeneous function is called homogeneous differential equation. That is, if I take a differential equation of first order and first degree equals this. This is called homogeneous differential equation if this function is a homogeneous function, which we have discussed in the recent session. Is homogeneous function. If f of xy is not a homogeneous function, then this differential equation is not a homogeneous differential equation. For example, dy by dx equals x square minus y square by xy minus x square is an example of a homogeneous differential equation. It's a homogeneous differential equation of degree 0 because this function has degree 0 is how we understand. And let's take another example. This is not a homogeneous differential equation because this is not homogeneous, as highest powers is 1, 1 and this is 0, so they are not with equal powers. Therefore, this is non-homogeneous function. Therefore, given differential equation is not a homogeneous differential equation is how we understand the homogeneous differential equation and a non-homogeneous differential equation connected with the homogeneous function f of x comma y. Now let's see how to solve a homogeneous differential equation as the second method of solving the linear differential equations. The second method is about solving of homogeneous differential equations. So let's see how we can solve using its respective method of solving. Say for example, I take a homogeneous differential equation dy by dx equals y square minus 2xy by x square minus xy. So clearly the right hand side is f of xy, which is a homogeneous differential equation of each degree 2, 1 plus 1, 2, 2 and 2, and therefore this is a homogeneous differential equation of degree 0 on the whole. So let's see how we can solve this homogeneous differential equation. Now In order to solve the homogeneous differential equation, the first step of solving using this method is that I take y equals some v times x, where v is a new variable introduced in the form of y equals vx. That implies differentiating on both sides, I get dy by dx equals d by dx of vx, which is using the formula u dash v, I get v times of d by dx of x plus x times dv by dx using this formula. So we get y is this and dy by dx is this, so that when substituted into equation 1, the whole of y is eliminated and we get the whole of equation gets reduced in terms of v and x. That is, the dependent variable y is eliminated, reduced to v and x. Therefore, substituting in 1, we get dy by dx, which is v plus x dv by dx, that is equal to y squared, which is vx whole square, minus 2xy, which is vx. So substituting in place of y, we get this as x squared minus x times of y, which is vx, is what we get. Now this, on further simplification, gives v plus x dv by dx, and taking v squared common on both sides, taking x squared common on both sides, 2xy v squared minus 2v by taking x squared common here, this is 1 minus v, is how we get by taking common on the numerators and the denominators respectively. So this gets cancelled and this gets reduced as v times of v minus 2 by 1 minus v is what we get on simplification. Therefore, taking this to the right, x dv by dx is equal to v times of v minus 2 by 1 minus v minus v, is what we get when we bring plus v to the right. And taking LCM, we get v times of v minus 2 minus v times 1 minus v by 1 minus v. This, on further simplification, gives v times of v minus 2 minus 1 plus v by 1 minus v. This, on further simplification, gives v times 2v minus 3 by 1 minus. So we get this as v times 2v minus 3 by 1 minus v, and therefore continue from here. I have x dv by dx equals v times 2v minus 3 by 1 minus v. So here now we are going to separate this into variables. That is, we are going to use variable separation method, where all v terms are brought to left and x terms to the right. One minus v by v times 2v minus 3 is equal to dx by x, is what we get. So taking common here, I get this to be minus of v minus 1 by v times 2v minus 3 is dx by x.